and 1, all powerful numbers. All computer data has to be converted into a long series of zeros and ones, whether it's for images such as computer graphics or for sound such as compact discs. But new recording techniques don't only depend on zeros and ones. They also rely on the magic of the laser, with which objects can be reproduced in 3 dimensions, holograms. Through television, we have become familiar with the new world of image making, computer graphics. Computer graphics create objects in 3 dimensions. They can be static, but they can also be animated, moving about in space, swirling and twirling, and disappearing at will. Computer graphics always produce images of astounding technical perfection. However, it can be a Herculean task. To produce the opening of this program, for example, just 34 seconds of animation, the computer graphics expert worked 200 hours, and it took 350 computer hours. But as an art medium, even the most sophisticated computer will always need the sensitivity of a human being. Over the last few years, computer-generated images have become the window of digital technology. Video games, television, advertising expose us to the visual feats of computer graphics every day. Digital images have many other applications as well. They have invaded the laboratory and industry. Chemists use computer-generated 3-dimensional models to develop drugs. Geneticists translate their findings on the DNA molecule into digital images. Engineers use computer graphics to design and test mechanical equipment, parts, engines, and other devices. Computer-generated imagery is also an effective tool in education. Phenomena ranging from the infinitely small to the infinitely large can be made visible by the computer graphics imaginary camera. Computer graphics are also used to train people in fields where technological complexity is ever increasing. The latest versions of flight simulators, for example, use digital imagery to reproduce in real time piloting conditions in more and more complicated aircraft. In fact, computer-generated imagery has made its way into all spheres of activity where it is necessary to be able to visualize an object or an idea. To produce a digital image, a cathode ray tube is generally used. Inside the tube, 1 or several electron beams, depending on whether it's for black and white or a color image, are directed onto a screen which has been coated with phosphorus. When an electron beam strikes a thin phosphorus surface, the surface lights up. The electron beams scan the phosphorus coating from top to bottom, following a pattern of parallel horizontal lines. The scanning movement can be compared to weaving. When you weave, the patterns are created by several parallel strands. Each strand is divided into color segments. By coordinating the segments, you create the illusion of continuous lines. In a digital system, the image is woven by the electron beam. The desired pattern is obtained by the computer, which turns the beam on and off at different times during the scanning. In addition to controlling the electron beam, the computer stores in its memory the image obtained. In order to understand how the computer is able to memorize images, you have to know that the phosphorus coating on the screen is comparable to a matrix made up of tiny dots. Each dot is called a pixel. Each pixel is stored in the computer's memory in the form of zeros and ones. A luminous spot on the matrix corresponds to the number 1, and a non-luminous spot to the number 0. So when you ask a computer to recreate a drawing already made, the electron beam gives an impulse that causes a pixel to be illuminated if the number the computer reads in its memory is 1. Conversely, if the number read is 0, the computer will not activate the electron beam, and the pixel will not be illuminated. To create color, digital systems usually use 3 electron beams. They can activate light emissions selectively onto minute screen surfaces, each containing 3 different types of phosphorus, emitting red, green, and blue. The conjunction of these colors with the varying intensity of the dots are what create the illusion of all the shades. Today, highly developed graphic systems can generate over 16 million different colors and attain a definition comparable to that of 35mm film. They can also produce 3-dimensional animated sequences in which the detail of shapes and quality of movement are comparable to traditional film animation. To produce 3-dimensional animation by computer, the computer graphics expert must follow well-defined, precise steps. The first step consists of designing each place and each object within a mathematical world. All these 3-dimensional elements are made of polygons, that is, of multi-sided surfaces. The polygons are connected together at their tops, the vertexes. Next, the expert determines the point of view that an imaginary camera would have on these objects. This sets up an initial frame, and the expert can then decide to change the imaginary camera's movement on the objects. The objects will all move about realistically, as if filmed by a real camera, or conversely, according to the computer graphics expert's creative fancy. When the computer graphics expert is satisfied with the object's shape, the camera's movement, and the set, she then adds the finishing touches of color and texture to both the objects and the background. The expert then determines the theoretical sources of light that will give the scene life. When a sequence is completed, it is transferred image by image from the computer's memory to a videotape. Every second of animation consists of 30 different images which, passing on the tape, will create the illusion of movement. Computer graphics is both an artistic and a scientific instrument with virtually boundless possibilities. When computer graphics first came onto the scene, it was thought by some that real actors and actresses would be replaced by computer graphic characters. They couldn't have been more mistaken. A few computer-generated characters were created, but never one who could dethrone Marilyn Monroe. However, it does seem that new recording techniques will indeed dethrone old methods. Our ears have become accustomed to a very high quality of sound. I cannot be the only person who is sorry that Maria Callas died before the compact disc was launched on the market. Sound is a wave that travels through a medium, usually the air, until it makes our eardrum vibrate, somewhat like the membrane of a drum. Traditional recording techniques reproduce sound waves via undulations drawn inside a groove. But the compact disc revolutionized all that. No more stylus, no groove, and the sound wave itself is converted into a binary code. That is, a succession of zeros and ones. For over 100 years, music was imprinted onto records in analog fashion. That is, in the form of undulations reproducing electromagnetic waves. But since the early 80s, the CD audio disc or laser disc has gained such ground that most multinationals have stopped making records on vinyl completely. On a laser disc, sound is not recorded in an analog way, but digitally. This means in the form of ones and zeros, just like in computers. Unlike your traditional vinyl record, the laser disc is virtually impossible to wear out, since there is no mechanical contact between the disc and the playing system. The player consists of a laser beam source, which scans the tiny grooves of the disc, one after another. The laser beam bounces off the reflective surface of the disc and is received by a photodiode, that is, a minute electronic tube that is sensitive to beams of light. On a laser disc, the digital information in zeros and ones is recorded in microscopic pits and flat surfaces. The flat surfaces and pits reflect light to the photodiode, which, stimulated, produces a short electrical impulse. When the light hits one of the pits, the light reflection is delayed. The light beam is decoded differently by the photodiode depending on whether it is reflected by a flat surface or a pit. The series of variations of the light beam corresponds to the zeros and ones. The digital information produced by the photodiode reverts back to analog form when it leaves the laser player. The reconstituted sound then continues its course through the various elements of a stereophonic chain. Despite its small size, namely 12 centimeters in diameter, a laser disc can hold over 1 hour of music. All this is made possible by sound digitizing. To digitize sound, sound waves are broken down. Every second of music, which initially is presented in the form of a continuous line, is broken into some 44,000 segments. Every segment receives a digital value consisting of a series of 16 zeros and ones. The sound digitizing process can be done in the recording studio or at the Laserdisc manufacturer. The first step is the cutting, which consists of transferring the digital sound data from a master magnetic tape to a glass disc coated with a thin layer of a light-sensitive material. The digital data on the master magnetic tape is forwarded to a laser beam generator. This light source burns the photosensitive layer at very specific points. A laser disc can contain hundreds of thousands of tiny pits. The cutting procedure is done in a strictly controlled environment. The technicians wear special suits, and the ambient air is filtered so that dust particles do not get into the microscopic pits on the disc surface. The operation is carried out under a yellowish lighting. Normal lighting could alter the master disc's photosensitive coating. Once the cutting, or imprinting, has been completed, the master disc is coated with a thin layer of silver. Next, matrices are made which will be used for the molding. The matrices are obtained by plating the master disc with a layer of nickel. Then comes the pressing operation, which is carried out by a robot production unit. A transparent plastic, polycarbonate, is heated to the point of liquefaction. The liquid polycarbonate is inserted into a pressure mold between the nickel matrix and a perfectly flat surface. The result? A transparent plastic disc with all the digital information contained on one of its sides. The plastic disc is then covered with a layer of aluminum, which will reflect the player's laser beam. The final touch is a coating of varnish that will prevent the aluminum from oxidizing. After quality control, the discs are packaged and marketed. The time is coming to an end when sharp-eyed music lovers could impress their friends by recognizing a recording of Ravel's Bolero simply by studying the record's grooves. Someday, all our vinyl records will be collector's items. Some objects disappear. Others become part of our daily lives. 10 years ago, the first holographic images were still a source of amazement. Today, they can be found everywhere, on book covers, jewelry, even on clothes. There's something disturbing about a hologram. Each of its parts contains the whole of the information on the object. For instance, if you break the hologram of an apple, in every little fragment, you will see the entire apple intact. Holograms are as mysterious as they are fascinating. As art objects, holograms have become part of our everyday life. Holography, like photography, records an object, a person, or a scene on film. But unlike photography, holography captures reality in 3 dimensions. That is, it records depth. Thus, when you look at a hologram, the subject appears to be right there, in front of your very eyes. To create a hologram, an object is illuminated by a coherent beam of light produced by a laser beam. This light is pure, that is, only contains 1 wavelength, hence 1 color. Moreover, the coherent laser beam does not move about incoherently in space, as ordinary light does. The waves of coherent light move in phases, the ups and downs meshing perfectly together. This phenomenon can be compared to a marching army, where the soldier steps hit the ground with perfect synchronization. The laser beam is produced by the stimulation of the atoms of a solid material, like ruby, or a gaseous material, like a mixture of helium and neon. The stimulation can be an electrical current or a flash of white light. The atoms excited by the electric or light energy produce photons or light particles. The photons in turn excite other atoms, which produce more photons in a rapid chain reaction. Photons reflected between 2 parallel mirrors produce a monochromatic light wave composed of waves of the same phase. But one of the mirrors of the laser generator is not perfectly reflective. When the light wave is bright enough, it goes through this mirror, producing a laser beam. That is a narrow, intense beam of light. A helium neon laser is often used to create a hologram. The whole technical installation must rest on a table, isolated from the slightest vibration. Stability is a prerequisite for making a successful hologram. To create a hologram, the laser beam must be divided in 2. An optical divider splits the beam into 2 perpendicular beams, the reference beam and the object beam. A mirror directs the object beam toward a concave lens that diverts the light to the object. The object then reflects the light waves whose intensity varies according to the shape and nature of the object. Part of the light waves will hit the photographic plate. Simultaneously, a mirror directs the reference beam to another concave lens that also reflects the beam. On the photographic plate, the 2 beams create an interference pattern, exposing the plate at points where they arrive in phase. These points correspond to the depth and dimensions of the object. The resulting hologram recorded on the photographic plate is somewhat like a negative. It can only be seen under coherent light of the same frequency as that used to form it. Like in photography, a copy of the basic hologram must be made. This copy will be visible in ambient light. Holography has many technical and commercial applications, but its pioneers want to go further than that. Research is already underway to produce animated holograms. Has it ever occurred to you that the same laser beam that reads your compact disc is also responsible for destroying malignant tumors and for the Star Wars killer beams? As other modern technologies, laser beams can be harmless or very destructive, depending on how they're used.